Chapter 20, slides 6 through 10. Okay, we're going to start with the acid chloride as the functional group that we're going to do chemistry on. So we're going to begin with a general acid chloride. And what we're going to do is show you a bunch of different nucleophiles that can be added and go through the effects of mechanistic effects of what occurs, and then see what product we end up with at the end of this. Okay, so we're going to go through acid chloride as the starting material for multiple different nucleophiles. You ready? All right, let's start with water. This is one of the reasons why if you make an acid chloride or buy an acid chloride commercially available, they're so reactive. Remember that the carbonyl is extremely electropositive. It's the most electropositive of all of the carbonyls I showed you. So you don't need a strong nucleophile to get this carbonyl to go. So I'm showing here a weaker, what we would deem a weak nucleophile, right? Water. It's neutral. And even water, I mean, moisture in the air can react with this starting material. So if you bought a bottle of this and you opened the bottle and exposed it to just maybe even just the humidity in the air, this molecule is going to react and degrade over time because it's going to react with even just the water in the air, the moisture. We tend to keep these starting materials, acid chlorides, if we have to keep them for a longer period of time, in a refrigerator or freezer. In the best case scenario, you would make or buy this material and use it immediately, because any length of time exposed to moisture and anything else is just going to react with it. So this is a 1,2 substitution. The partially negative oxygen is going to react with the carbonyl in and up. If I have to describe every arrow that I'm drawing, so like in this first step, it goes in and up. Remember, the carbonyl started as a carbon that was sp2 hybridized. And when the water attacks, it can attack from either the front side or the back side. You're going to see that it won't matter here. And now the oxygen has a negative charge. Now, the oxygen can come down and out if there is something other than carbon or hydrogen available to push out. So of these two, the chlorine is a fantastic leaving group. And so we're going to continue with this intermediate, having the oxygen push its 2 electrons that it just gained back down, but we're going to kick out the other group, the good leaving group. We've seen chlorine be a good leaving group, right? SN1, SN2, E1, E2. And so in this step, we regenerate the oxygen double bonded to the carbon, but now we have a different group flanking off to the side. And yes, chlorine minus is the leaving group. Now, at this point, there's nothing more that we can do. You might say, well, can't water attack the carbonyl? Sure, water can attack the carbonyl. So I'm going to do an aside. If water attacked the carbonyl at this point, what would we get? You could argue, well, the carbonyl is partially positive. It's less positive than the acid chloride was. And we have a weak nucleophile. But just for argument's sake, let's just push the electrons in the in, up, down, out scenario that we just saw. if you take a look at this point, after in, up again, remember we did down, out. If there's something other than carbon or hydrogen, right? Well, we've got water and water. There's something other than carbon or hydrogen, and it's a good leaving group, right? We saw water as a leaving group in the SN2 reactions, or the SN1 reactions and E1 reactions. So it's gonna come back down. Does it matter when it comes back down which one it kicks out? No. So let's say it kicks out the original one. I mean, who knows which one that is? When down out ensues, guess what you get? The same thing. So is this happening continually? Maybe, but it's not going to change what you get. So even if you kept doing the water attacking the carbonyl, it's still going to keep giving you the same compound. Therefore, all that's left at the end of the day is to work it up. What kind of workup do we need? Well, we need maybe some sort of base. But what's happening is that the water is probably going to abstract the extra proton. And so if water, because that's what's floating around, if water takes off, because we got lots of it, right? If water takes off the extra proton, you end up with a carboxylic acid and H3O plus, which is an acid. So, and that's a strong acid. Hydronium ions, H3O plus, are strong. So the workup that you would need is some sort of weak base. You don't want to overdo it. You just need to take off a little extra of the proton, make the acidity of the solution come down just a little bit towards, come up a little bit towards the 7 mark, but it's never going to be neutral. And the reason it's never going to be neutral is because you're generating a carboxylic acid as the product. So you went from an acid chloride to a carboxylic acid. So we can go from one functional group to another. In, up, down, out is the key to this 1,2 substitution. Let's try another one. Let's start with an acid chloride and react it with, how about ethanol? Again, the carbonyl is extremely electropositive. We only need a weak base or nucleophile in this case. So the nucleophile is the ethanol, the oxygen's partially negative, and we're going to go in, up. So the electrons of the oxygen make a bond to the carbon of the carbonyl. The carbon-oxygen double bond, the pi bond breaks. That's the weakest bond. Think about strong bonds are sigma bonds and the weaker bonds are pi bonds. So the pi bond, which just has parallel overlap, is the one that breaks and goes up. Those electrons go up into the greedy oxygen. So let's draw the intermediate. Again, this could happen from the front or back side, but it doesn't matter because the electrons end up coming back down. Why? Because we have a good leaving group, chlorine. So the electrons won't stay here. They're going to come right back down and kick off the good leaving group in a down-out part of the reaction. And this is my description. I call this the in, up, down, out reaction. I like having ways to describe what we see. And yes, the chlorine has gone away. You could argue, hey, why doesn't the chlorine grab the hydrogen? Why is it more likely that the alcohol grabs the hydrogen? Well, if you think about it, in this workup, either way you look at it, you're going to generate this new system. And you could say that the ethanol is what grabs the extra proton, and I'm under acidic conditions. Between the chlorine and the oxygen, chlorine is the more stable negative charge. There's probably a lot more ethanol floating around. So from a concentration perspective, there's a lot more ethanol molecules floating around. And then there's fewer chlorine molecules. Okay, but could chlorine be the base? Well, chlorine's a terrible base. Why? Because it's so stable when it grabs those electrons. A good leaving group is a good leaving group because once it leaves, it's stable enough to just be on its own. It's what makes a good leaving group a good leaving group. It leaves and it doesn't come back to interact. The best leaving groups go away and stay away. So chlorine minus is really greedy. So it's an atom that can very easily stabilize that negative charge. And so once it's gone, it's not desperate to react with anything. The oxygen carrying the extra proton needs to be worked up, and it has a better likelihood of being deprotonated by the solvent or the ethanol itself. Or just, if you came in and just added a weak base for the workup, you could have also written the base that you used as the workup coming in. Either way, it really doesn't matter. At the end of the day, we have formed an ester. And if you came in with a weak base, the weak base would deprotonate and neutralize the protonated ethanol. Either way you look at it. Do we really know what's happening? Yeah. It's going to generate a little bit of acidic media as this reaction ensues. However, it's not going to stay as the protonated system if we come in with a weak base to neutralize everything. So this is the workup step. Either way you look at it, you're going to need a weak base to either neutralize the protonated solvent that you used as the base, or just in itself, you could skip this step altogether and say, the workup. If you want to just write it that way, I'm fine with that. The weak base comes in and deprotonates. But it's probably not the chlorine. Okay, and now we've converted an acid chloride into an ester. 1-2 substitution. In, up, down, out. Let's do another one. How about we start with an acid chloride again? And this time, let's do, I don't know, diethylamine. Okay, any amine. I could have done ammonia, right? But I'll just use diethylamine. And we're going to do in up, because again, our carbonyl is electropositive. The nitrogen's lone pair attacks and makes a bond with the carbon from the front or the back side. And the pi bond is the weakest bond. It goes up to the greedy oxygen, electronegative oxygen. Take your time. Write them out. We just formed our tetrahedral intermediate. Stop and look around. Do you have a good leaving group? Yep, I do. Chlorine. Down and out ensues. And overall, we get our 1-2 substitution. At this point, again, amines, you can think of it this way. Amines are bases, right? Amine base. So starting material itself could act as the weak base to take off the extra proton and give the electrons back to the nitrogen. And you're going to form a mildly acidic system that you would have to work up with a little bit of weak base anyway to get things back to neutral, right? Because the chlorine is still around too. So you're forming an ammonium chloride salt. And that could go into the water layer. If you added enough, if you added excess of the starting material, you'd kind of be working it up at the same time anyway. And the salt, right, could go into the aqueous phase. So if you add enough of your starting material in this case, it is a weak base in and of itself. So you don't have to do very much. It's already going to form your salt and go into the aqueous layer. So you're probably fine if you just add an excess of the starting material. But we have gone from an acid chloride to an amide. Now, I also want to point out to you that the leaving group in all of these cases has been chlorine. Because chlorine is a great leaving group, it is not going to go back. So it's not going to attack back and get back to the starting material. Why? Because once it leaves, it leaves. It's gone. Therefore, I want you to pay attention to the arrows that I've used. Once you react an acid chloride with something and exchange the chlorine for something else, right? You're substituting the chlorine for some other group. Once you've done that, because chlorine is very greedy and happy with the negative charge, you're very unlikely to go back. So these are not reversible reactions per se. Okay, so you can pretty much uniformly in one direction, straight arrow, go from the acid chloride to the amide. This is not a reversible reaction. Okay, again with the same type of unidirectional arrow. Notice that the flashcard changed a little bit here. What's happening? Well, I'm now going to introduce you to some reagents that you're less familiar with. The next two flashcards are reagents that we haven't seen yet. The first one that we're going to do is LAH, or lithium, aluminum, hydride. Ooh, there's a word we know, hydride. What is a hydride? Well, lithium aluminum hydride looks like this. It's aluminum, which, as you know from chapter 1, aluminum is in group 3. So it's 1, 2, 3. Its bond trend is 3 bonds, no lone pairs. So when aluminum has 4 bonds, it's negatively charged, and therefore it's an ion. The counter ion is lithium. So lithium aluminum hydride. What this means is that aluminum is not very happy with the 4 bonds. It thinks it wants an octet, but it's not happy with it. So in solution, what's going to occur is that the aluminum needs to get rid of one of the hydrogens. So you can think of it as these electrons leaving. It's kind of weird if you think about it. But a hydride is an H- because the hydrogen has left with its 2 electrons. So whenever you have a hydrogen and 2 electrons, it is a hydride. And we have different forms that we can purchase so that we can use H- as a nucleophile or a base. So hydrides are really interesting because they can be our base or nucleophile, and we can purchase them. We can buy lithium aluminum hydride. It comes as a salt, and then when put into solution, it can dissociate its H- and give us an H- source. They're very reactive. You got to keep them very dry. They are, an H- is a highly reactive species, and so you want to be very careful with them. You want to work under atmospheres that are not moist. So we've got our very electropositive carbon. We have our now strong nucleophile. I'm just going to shorthand lithium aluminum hydride. Say it out loud. Lithium aluminum hydride. The H there means hydride. That's the H. So our H minus is strong. And then these electrons are desperate, and they're going to find the electropositive carbon. In up, the electrons of the pi bond break, and they go into the greedy oxygen. The pi bond is the weakest, which is why that one is the one that breaks. Now take a look at what we've just done. We have added a desperate hydrogen to the carbon of the carbonyl. Of all of the bonds that could break from the intermediate, the down out is going to be very specific. It is only going to want to down out with one thing, and that is the chlorine. So the oxygen comes down with its electrons, and it's going to kick out the aldehyde, or sorry, the chlorine, forming an aldehyde. Interesting. Now, aldehydes, if you recall, are the next most reactive carbonyls. And floating around is H minus. Once you form one of these aldehydes, they are equally as capable of reacting with an H minus. So notice that what I've just done up until this point, this aldehyde, is something that, could be stable along the way, but it's a train you can't stop. Because of the whole solution, you can't say, oh, hydrides, ignore the product you just made in solution. It can't. It's going to start seeing product. It still sees starting material. The H minus is going to be attracted to to both of them, and it's just a train you can't stop. So it just keeps going. So we're going to do another in and up. Compare this step with the previous one that we saw. When we were looking at the acid chlorides with water, I had an aside where I kept adding oxygen. I put oxygen on, right? In, up, oxygen on, down, out, kicking another oxygen off. So understand that when you're adding a group like oxygen or nitrogen, those groups can potentially come off. They're removable. They're not carbon, they're not hydrogen. So even though this aside down here on the bottom was probably happening, you're never going to see the result of it because you keep regenerating the compound you would have if you never did it anyway. So if you just tried to keep adding water on, in, up, down, out, in, up, down, out, you're just going to keep getting the same product. In this case, if I do in, up, down, out, and then do it again, I'm actually not going to get the same product, nor am I ever going to be able to get back to the acid chloride. So understand at this point, I'm going to draw an arrow, but I'm going to erase it because down and out, is hydrogen a good leaving group? Absolutely not. So we can't see that. It's stuck in a new intermediate. And so there's there's nowhere to go anymore. So all we have to do is work it up. Now let's consider the workup here. What kind of workup do I need? Acidic or basic? Two ways of looking at it. You can look at the needs of the intermediate and say, boy, I really need a proton to, cap that oxygen and make it neutral again. And you'd be right. So you need some sort of weak acid for acid-base chemistry, so that the oxygen can get protonated and give me a neutral species. I've just made an alcohol. Now, understand that if you look back at the reagents, I was operating under a strong nucleophile conditions, which strong nucleophile is also a base, right? I mean, what makes a base or a nucleophile strong is it's got a formal negative charge. So I was operating under very basic conditions because I was working under strong nucleophile base conditions, H minus. So to work up, it's usually the opposite, right? I need to neutralize everything. So to get back to neutral, I need to work it up with some acid to neutralize everything. So this is how you would go from an acid chloride using lithium aluminum hydride to get to the alcohol. Let's go back and consider our oxidation reduction ladder here. We went from something like an acid chloride. Oops. I'll use this one, acid chloride, where I had 2 CO bonds, and I reduced it using a hydride to get to an alcohol. Notice that the reduction is the gain of CH bonds. So the way we tend to do that, to reduce, if I need to add more CH bonds, H minus as a nucleophile or a hydride is one of the typical sources we will use to go down the ladder in reduction. I'm adding H's, adding H's, adding H's. So I just wanted to make sure you see how this is reducing our system. The last one we're going to discuss is how to make carbon-carbon bonds. Now, this is a special reagent, but it actually does not require you to think beyond what you already know. Okay, we're going to start with an acid chloride. We're going to see the same mechanism we just saw. We've got a good leaving group, right? The chlorine's a good leaving group. The carbonyl is a fantastic electrophile. It's super electropositive. And we're going to introduce a reagent that's ionic, strong nucleophile. Let me give you an example. CH3, magnesium, I'll use chloride. You could use bromide, you could use iodide. Let's break down what this is. This is called a Grignard reagent, named after the scientist who discovered these reagents and used them effectively. Remember I said anything with a name, Grignard, it's usually because you've made new carbon-carbon bonds. That is the key. That's the secret sauce to organic chemistry. So a Grignard reagent is basically a carbon minus. So a carbon with, say, 3 bonds and a lone pair, not a carbocation. This carbon has an octet, but it's a carbon minus because it has a lone pair. You can't just buy carbon minus. That's very unstable, very highly reactive. It comes as a salt, which is, again, the salt is very highly reactive, but you have to buy it on the shelf, right, as some neutral species. So the magnesium is a counter ion, and the magnesium usually loses 2 electrons, making it +2. Well, we're not neutral yet, right? We still have overall -1 + 2, that's -1 still. That's where the other halogen comes in. Chloride is in its negative state. So together, this makes a neutral salt. But don't be fooled by the fact that it's a salt. Because it's carbon minus, this is a highly reactive, just like the H minus, a very highly reactive species. It comes, again, in a bottle that's sure sealed, so there's no air or moisture in it, because it will react with air and moisture, and you'll just degrade your reagent into something that's non-reactive anymore, because it's just going to find a proton to react with somewhere, wherever it can desperately. So you can buy these salts in, you can buy methyl magnesium chloride, you can buy ethyl magnesium bromide, you can buy an array of different carbon minuses, and they're called Grignard reagents. But you can think of them as just carbon negatives. And this carbon negative is going to find the very electropositive carbon. Guess what? Are you bored yet? In and up. We form the tetrahedral intermediate. I've just added a methyl group. Sure enough, because we've got a good leaving group, that tetrahedral intermediate isn't going to stay put because the electrons will pop right back down and kick off the good leaving group. Down and out. Regenerating the carbonyl. I'm going to number my atoms. 1, 2, 3. 1, 2, 3. Notice I just made a ketone. Ketones are reactive, right? Is the chlorine minus going to come back in? Heck no. It is not a good nucleophile, so it stays gone. But maybe you've got some methyl magnesium still floating around. If it only reacted with one, it now has competition. The product is reactive just like the starting material. It's not as reactive, but it's a hard train to stop. Typically, when people run these Grignard reagents with an acid chloride, you just add enough to make it continue all the way to the end. So you might add 2 equivalents, enough to add to the acid chloride, then enough to add with the resulting ketone, just because it's kind of too hard to control and you'll get a mixture. So let's just keep going because we can. The negative carbon attacks the ketone again, and the pi bond breaks, and it undergoes another in-up reaction. Just keeps going till it can't go no more. Right, so I added another CH3, just like the others. Can the electrons come back down? Nope. So it's stuck here in this tetrahedral intermediate. It can't come down because if it comes down, it would have to kick out, pick one, anyone, it would have to kick out a carbon. That's not going to happen. So it's stuck. And all we have left to do is acid-base workup. And again, I'm going to need some sort of acid. Think about what you were working under. You were working under strong nucleophile, which also means strong base conditions. So it makes sense that the workup would have to be acidic to neutralize everything. And I made an alcohol. But one of the take-home messages to this one is that I added, so I started with, say, 1, 2 carbon. 1, 2 carbon. And in the end, I added a 3rd and 4th carbon to the system. T-butanol in this case. But at the end of the day, take a step back and look, we've done nothing but do unidirectional in, up, down, outs all the way through.